Chapter 8, Surface Water Hydrology. So the topics we cover in this session are peak flow calculation methods, a CSTP 149 method, FHWA HDS2 peak flow design method, discharge area and regression formula. We cover Cypress Creek formula, and then we cover USGS regional peak flow regression equation, and finally we cover snowmelt hydrology. Peak flow estimation is CSTP 149 method. So that is for soil conservation services, technical paper 149. Input, you put drainage area, average watershed slope, storm distribution type, and depth of rainfall. There is graph here, TP 149 peak rates, as you see here, at horizontal axis, that is drainage area. At the left, you see peak discharge in CFS. And as you see inclined lines, so you see for 24-hour rainfall, and it starts with 12 inches and goes to up to 1.4 inches at the right. Charts available for peak flow estimation, storm distribution type for type 1 and type 2, slope type that's flat for 1% slope. Slope range is from 0 to 3%, curve numbers from 60 to 90. So the same for storm distribution, type 1 and 2, but the slope were from 3 to 8%, and again from 60 to 90 CN curve number. And at the bottom, you have for slope and for steep 16% slope. Number 2, FHWA HDS 2 peak flow design method, that is for Federal Highway Administration. QP equals to QU times A times Q. This formula here, as you see, Q equals this formula. QP is the peak discharge in meters cubed per second. A is the drainage area in kilometers squared. QU is the unit peak discharge. Q is the rain depth in millimeter, and TC is the time of concentration in hours. So you can use coefficient for FHWA HDS to SCS peak discharge method. So you can find for rainfall type 1, type 2, type 3, and type 4, IA over P, C initial, C1, and C2. You can use these coefficients and constants, and you can plug in the previous slide to find Q. Limitation. There are some limitations. Use the homogeneous watersheds. Curve numbers from zone to zone should not differ by 5. Curve number should be greater than 50. Time of concentration, or TC, should be between 0.1 and 10 hours. IA over P should be between 0.1 and 0.5. TC, time of concentration, should be about the same for any of the main channels if the watershed has more than one main channel. No channel or reservoir routing is allowed, and no storage facility on the main channel is allowed. Watershed area in storage ponds and lakes should be less than 5%. These are limitations on using this method. Discharge area regression formulas, the same as what you do in other classes. You can use regression formula to derive your own formula. Here you use Q equals to C times A to power M. Q is the peak discharge associated with a given return period. A is the drainage area. C and M are regression constants. For example, you see this formula, Q equals to 10,000, A to power 0.5. A is the drainage area, and that must be in 4 miles squared or more. And Q is the ultimate maximum flood flow in CFS, feet cubed per second. So if you have, as you see here, if you plug your area here, you can find your Q, which Q is ultimate maximum flood flow. Cypress Creek formula, Q 24 hours will be CA 5/6. Q24 is required channel capacity for 24-hour removal. And CFS, C is drainage coefficient, that's constant number. A is drainage area in miles squared. And C equals to 16.39 plus 14.75 QSCS. And what is QSCS? QSCS is the SCS direct runoff in inches for 24-hour design event. And QP over Q24 hour will be 2 minus 0.43 log A. So you can find, first you find Q24, and then you find QP, which is QPIC. So here's the graph in horizontal axis, that's time. In vertical axis, we have discharge rate. And then you see here duration of overbank flow and inflow hydrograph. At the left, instantaneous peak at the top, and at the right, drainage ditch capacity based on removal rate. USGS original peak flow equation. This is another method that we use. Considered parameters. These are our parameters. Drainage area, basin slope, watershed aspect, elevation, mean temperature during snowmelt session. These are our parameters. Equations for all states available in the package of NFF stands for National Flood Frequency in USGS. Here, as you see, this is for Texas regions. Introduction to hydrology. This is the reference, but as you see, the numbers are for Texas. So example, develop equations for region 2. You can use Q2, Q5, Q10, Q25, Q50, and Q100, where Q is peak discharge, A is drainage area, and S is average slope. Based on this, you can find these Qs for Texas. Snowmelt hydrology. So we have to see how we can find the answer for snowmelt. First is radiation melt, D12 equals to D initial 1 minus 0.75 times M. D initial is snowmelt occurring in a half day in clear weather. M is the degree of cloudiness. So 0 for clear weather, 1 for complete overcast. D initial is 0.35 for March, 0.42 for April, 0.48 for May, 0.53 for June. That's for latitude of 40 to 48 degrees. Condensation melt. So condensation melt, you can find D equals to K1 times V times EA minus 0.6.11, where V is the mean wind velocity. It should be in miles per hour. You have to be careful. It should be in miles per hour. EA is the vapor pressure of the air in MB. So it is an MB. So convention melt. D equals to KVT minus 32. So where V is the mean wind velocity in miles per hour and the T is the temperature in Fahrenheit. Rainfall melt. M equals to P times TW minus 32 over 144 QT, where P is the rainfall in inches and TW is the wet bulb temperature assumed to be that of the rain in Fahrenheit. Example, there is one example here, problem 8.11. So given drainage area is 45 acres and curve number is 70, type 2 storm, P50 is so 8.6, so P100 will be 9.4. Try to use the curve that I showed in previous slides and find the numbers. So from the figure, 8.9 Q50 will be 150 CFS and Q100 simply will be 185 CFS. Example, during a completely cloudy April period of 12 hours, the following averages existed for a snowpack located at 10,000 feet above sea level at a latitude of 44 degrees north, air temperature is 50 degrees of Fahrenheit, mean wind velocity 10 miles per hour, relative humidity is 65%, average rainfall intensity is 0.03 inch per hour. For 12 hour wet bulb psychrometric reading is 48 degrees of Fahrenheit, and QT constant for this problem is 0.097. And this is the what we need. So determine this normal in inches of water for radiation, condensation, convection, and warm rain for 12-hour period. So I need you here to pause the video and open your notes and go back to previous slides and find any of the formula that we need and use it here. The first is radiation. The formula for radiation is D12 equals to D initial times 1 minus 0.75 times M. D initial, so you can find these numbers in your notes that I provided in these slides, or you can find in your book. D initial is 0.35 for March, but here our problem, as you see in the first line, that is for April. For April will be 0.42. So D initial is normal occurring in the half day in clear weather. M is the degree of cloudiness. So 0 for clear weather and 1 for complete overcast. So D12 will be 0.42. Why? Because D initial is for March, for April, and for April is 0.42. And then 1 minus 0.75 times 1. 1 is for complete overcast. So we find here radiation, using radiation, 0.11 inches. Number 2 is condensation. D equals to K1 times V times E minus 6.11. D will be 2 times 0.00578 times velocity was 10 times EA equals to 12.19, which there is a table at the end of your book. You need to go over there and table 8.2 for 50 degrees of Fahrenheit. You will find 12.19 for EA minus 6.11. That will be 0.21. Why you have times 2 here? That is the formula is for 6 hours. The problem asking for 12 hours. You need to multiply 2, and K1 will be 0.00578. Convection. Convection D equals to KVT minus 32, and K equals to 0.7 at 10,000 feet. There's formula in your book. I recommend to find the formula in your book and plug 10,000. But if you plug it, that will be 0.7 times 0.00184. So it will be 2 times 0.7, because that's in 10,000 feet, times 10, that will be the temperature 50 degrees of Fahrenheit, will be 50 minus 32, and the answer will be 0.46 inches. Rainfall melt, the last one, the formula is PTW minus 32 over 144 QT. So M will be, P will be 0.03, as you see, if you go back to problem statement, that is inches per hour. But P stands for total precipitation, 0.03 times 12 hours, times TW is 48, is given in your problem statement, minus 32 over 144, and QT is given here, 0.97. The answer will be 0.04 inches. So there is problem in your book, problem 8.1. So stop your video here and try to read the problem and answer this problem. During a partly cloudy April period of 12 hours, the following averages existed for snowpack located for 10,000 feet and at the latitude of 44 degrees of north, and the air temperature is 50 degrees, mean wind velocity 8 miles per hour, relative humidity 65%, average rainfall intensity 0.04 inches per hour for 12 hours, and wet bulb psychrometric reading is 48 degrees of Fahrenheit. Estimate the snowmelt in inches of water for first, number 1, radiation, number 2, condensation, number 3, convection, number 4, warm rain for 12-hour period. So I need you to stop here, go back to previous problem, and same as that problem, solve this problem. So first is radiation. The formula for radiation is D12 equals to the initial 1 minus 0.75 times m. Again, we have here, the problem is asking for a partly cloudy April. So the initial for April is 0.42. The initial is this normal occurring in a half day in clear weather, m is the degree of cloudiness. So here D12 will be 0.42, same as previous problem, 1 minus 0.75 times 0.5. Why 0.5? Because it says partly cloudy. So we consider 0.5. So 0 is for clear weather, 1 is for complete overcast. So we consider half. Number 2, condensation. D equals to K 1 times V times EA minus 6.11. So from here, D will be 2 times 0.00578 times velocity is given here. It's 8 miles per hour times 12.19 times 0.65. This is from table A2 at the end of your book. And 65%, that's humidity. So you will get here as 0.17 inches. Number 3, convection. Convection, again, constant K for 10,000 feet will be 0.7. D equals to KVT minus 32. I recommend to stop the video on any of these answers and try to answer, and then try to play the video to see the answer. So D will be 2 times 0.7 times 0.00184. That is this 0.7 times this number, that's for 10,000 feet, times 8 is the wind velocity, times 50 minus 32 will be 0.37 in inches. Rainfall melt, M equals to P times TW minus 32 over 144 QT. So P is here given 0.04 inches per hour times 12 hours times 48 minus 32 over 144. You can consider 0.97. This is not, if this is not given this problem statement or any other stated problems, you can consider this number will be 0.97. The answer will be 0.05 inches.